Good evening. Today we're talking about section 4.7, L'Hopital's rule, but continued. So we've already been introduced into the idea of L'Hopital's rule that if we have an indeterminate form, a 0 over 0 over or an infinity over infinity, we can take the derivative of the top and the derivative of the bottom and get something that works for us. But we can use L'Hopital's rule to do more with some kind of challenging indeterminate forms. So now consider limits of the form, the limit as x approaches a of f of x times g of x, where the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals plus or minus infinity. Such limits are denoted as 0 times infinity. And this is a really good question for what exactly do we do when we get something that looks like 0 times infinity. It's not straightforward. Does the 0 dominate? Does the infinity dominate? We will see. Now, L'Hopital's rule cannot be directly applied to limits of this form. Instead, we must recast whatever the limit we have into a form we know, like 0 over 0 or infinity over infinity. So let's start with a little example. I want to evaluate the limit x approaches infinity of x squared times sine of 1 over 4x squared. We know from previous work that as x approaches infinity, 1 over 4x squared approaches 0, and sine of 0 equals 0. So we've got something that looks like infinity, which comes from the x squared term, times 0. So we certainly need to do something about this. And the thing that we're going to do is remember that x squared is the same as 1 over x squared. And we're actually going to replace our x squared with this. So we end up with sine of 1 over 4x squared divided by 1 over x squared. And now we've got something that when we directly plug in, we get 0 over 0, which means we can use L'Hopital's rule. So in using L'Hopital's rule, we take the derivative of the top where we have to use the chain rule. So we get cosine of 1 over 4x squared times the derivative of 1 over 4x squared, which is 1/4, times the derivative of 1 over x squared, which is -2, times x to the power of -3. And all of this gets divided by -2 times x to the power of -3. And here it's pretty easy to see that we get to cross that term out, we get to cross that term out because we've got one copy on the bottom and one copy on the top. And our new limit looks like the limit as x approaches infinity of 1/4 times cosine 1 over 4x squared. And I'm going to take this and I'm going to copy it and bring it down to my next slide. So this is my new limit. And now we can just directly substitute. As we know, the limit of 1 over 4x as x approaches infinity goes to 0, and cosine of 0 equals 1. So this whole term becomes 1 times 1/4. There's no x's to plug in anymore, so our answer is just 1/4. So we were able to take something that we normally would have said is 0 times infinity and get an answer out of it, namely 1/4. So let's see what other sorts of things we can do. We can also deal with limits of the form infinity minus infinity. That is, the limit as x approaches a of f of x minus g of x, where the limit of f of x equals infinity and the limit of g of x equals infinity. These are indeterminate forms that we denote infinity minus infinity, and L'Hopital's rule cannot be applied directly to an infinity minus infinity form. It must first be expressed in the form 0 over 0 or infinity over infinity. So let's see what we have to do to work this example. Here's a little hint about what we're going to do. Occasionally, it helps to convert a limit as x approaches infinity to a limit as t approaches 0 from the right-hand side by a change of variables. To evaluate the limit as x approaches infinity of f of x, we define t to be 1 over x. And note that as x approaches infinity, t approaches 0 from the right. Then we have the following statement. The limit as x approaches infinity of f of x is equal to the limit as t approaches 0 from the right of f of 1 over t. So let's see if we can use this in our next example. I want to evaluate the limit as x approaches infinity of x minus x squared minus 3x quantity square root. So we can see that if we just directly substitute, we get infinity minus pretty much the square root of infinity. Which infinity is bigger, we're not really sure. So the first thing that we're going to do is actually mess around inside our square root. I can pull an x squared out of each term and I get 1 minus 3 over x, all under my square root sign. So I have something that looks a little like that. Now we know that the product of two things, if we take the square root, is the same as taking the square root of one thing times the square root of another thing. That is, I'm going to write this over here. The square root of a times b is the same as the square root of a times the square root of b. So I can take the square root of x squared and pull that out. And I get x minus x times the square root of 1 minus 3 over x. And in fact, I can pull this out further. And I get 1 minus the square root of 1 minus 3 over x square root. Now we have something that looks a little bit similar to what we were doing with last problem. I've got x times something. So I've got infinity times 1 minus some number. And in fact, we can recast this. X is the same as 1 over x. So we can rewrite this as 1 minus 3 over x square root over 1 over x. And now we're going to use that trick that we saw from earlier. We're going to let t equal 1 over x. And now we have 1 minus 3 times t square root over t. So our new limit becomes the limit as t approaches 0 from the right. From here, we've got 0, or we've got something divided by 0, pretty much. We've got 0 divided by 0 if we just plug in for a. So we can use L'Hopital's rule. And in fact, when we do that, we get the following. I'm going to abbreviate LH rule. We're still dealing with a limit in terms of t. We just get 3 over 2, 1 minus 3t, all over 1. And here's something that we can plug in 0 to. We're not going to get 0 divided by 0 error anymore. So when we do that, we get the square root of 1 minus 3 times 0. 3 times 0 is 0. The square root of 1 is 1. Our final answer is 3 over 2. So we see that just because we've got infinity minus infinity doesn't mean that we have something we can't deal with. We can always deal with it. We just have to be careful about what we're going to do. Now, there's more indeterminate forms that we can talk about, namely 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. And these all arise when we've got something that looks like the limit as f of x to the power of g of x for x approaches a, where x approaches a could be replaced with x approaches a from the left or right, or x approaches positive or negative infinity. Again, L'Hopital's rule cannot be applied directly to the indeterminate forms. They must first be expressed in the form 0 over 0 or infinity over infinity. So here's how we proceed. And this is actually a pretty neat trick, but it might be a little bit meaty, so feel free to watch this again and again, and feel free to shoot me an email if you've got any questions. We take note that the inverse relationship between the natural log of x and e to the x says that f to the power of g is the same as e to the power of g times the natural log of f. So we first write the limit as x approaches a of f of x times to the power of g of x. And we rewrite that as the limit as x approaches a of e to the power of g of x ln f of x. By the continuity of the exponential function, we switch the order of the limit and the exponential function. That is, our limit gets to move inside, and instead we have e to the power of the limit as x approaches a of g of x ln f of x. So we proceed using the following two steps. We analyze the limit, and we can put it in the form 0 over 0 or infinity over infinity. Then we can use L'Hopital's rule. And when L is finite, the limit of our function, f of x to the power of g of x, is simply e to the power of L, and we can just find that number. If L is infinity or negative infinity, then the limit of g of x ln f of x equals infinity, or the limit of g of x ln f of x equals 0, respectively. So let's go ahead and do an example. And this is something you may have seen, and you might be like, what, Emily, this is so crazy, but we're going to do it and you're going to feel confident about it. Or else. This is evaluating the limit x to the power of x. So when we plug in 0, we get 0 to the power of 0. And we know that 0 to the power, anything to the power of 0 is always 1. But we know that 0 times itself is 0. So what is more dominating, the 0 or the 1? And we're going to find out when we perform this. So let's get ready to rumble. Using the given two-step procedure, we note that x to the power of x is the same as e to the x ln of x. And now we need only find the limit as x approaches 0 from the right of x ln x. Now here we get 0 times infinity, which we can put in the form infinity over infinity by simply remembering that x is equal to 1 over x. So this becomes ln x over 1 over x. This is infinity over infinity, which means we can use L'Hopital's rule, LH rule. The natural log of x, the derivative is 1 over x, and the derivative of 1 over x is negative 1 over x squared. When we sort everything out, that is equal to the limit as x approaches 0 from the right of negative x, which equals 0. Now note that this is our L. This is a finite number. It's not infinity. It's not negative infinity. We just keep going. So we say we have the limit as x approaches 0 from the right of x to the x is equal to e to the L, which is equal to e to the 0. Anything to the power of 0 is equal to 1. That's how we find that answer. So let's keep going. What about 0 to the power of 0? Or, sorry, 1 to the power infinity. Our L is is the limit as x approaches infinity of x ln 1 plus 1 over x, which has the form 0 times infinity. Proceeding like we do in part A, this just becomes limit x approaches infinity ln 1 plus 1 over x of 1 over x. And now we can apply L'Hopital's rule. We get 1 over 1 plus 1 over x times negative 1 over x squared, all over, oh my gosh, I don't know how to fix this, all over negative 1 over x squared. These two terms cancel out. We're left with the limit as x approaches infinity of 1 over 1 plus 1 over x. That simply equals 1. So L equals 1. That means we need to go on to our second step. So the limit as x approaches infinity of 1 plus 1 over x to the x equals e to the L equals e to the power of 1 simply equals e. And something pretty cool, when we go to plot this function, I'll do it really quick. And you can check this using Wolfram Alpha or something like that. We actually have a horizontal asymptote at y equals e. I think that's pretty cool. So let's move on to the next thing that we can use L'Hopital's rule for. A particular theory for modeling the spread of an epidemic predicts that the number of infected people t days after the start of the epidemic is given by the function n of t equals 2.5 times t squared over e to the 0.01 t. In the long run, that's as t goes to infinity, does the epidemic die out or does it spread? That's the question we want to answer. If t squared grows faster than e to the power of 0.01 t, as t goes to infinity, then the limit of our function goes to infinity and the epidemic grows. However, if e to the 0.01 t grows faster than t squared, then our limit of n of t goes to 0 and the epidemic dies out. So what can we do to figure out which one happens? Our goal is to obtain a ranking system for the following families of functions based on their growth rates. So m times x, where m is greater than 0, represents linear functions. Think y equals mx plus b, where x to the p and p greater than 0 represents polynomial and algebraic functions. X to the x, sometimes called our super exponential or tower function. We want to know about that one. We want to know about the natural log of x, the natural log of x to the power q, or powers of logarithmic functions, x to the p times ln x, where p is greater than 0, which is a combination of powers and logarithms, and e to the x. We want to know what it means for one function to grow faster than the other function. So we work with the following definitions. Suppose f and g are functions with the limit of f of x equaling the limit of g of x equals infinity. Then f of x grows faster than g of x as x approaches infinity if g of x over f of x equals 0, or equivalently, if f of x over g of x equals infinity. The functions f and g have comparable growth rates if the limit of f of x over g of x as x approaches infinity equals m, where m is finite and non-zero. So what does this mean? Let's quickly look at some graphs. Here I've got x squared, x to the 4th, and x to the 6th. We say that x to the 4th grows faster than x squared because I can get the number 20 earlier on than if I was using x squared. So we have x squared grows slower than x to the 4th, which grows slower than x to the 6th. So here's kind of the idea, right? If we've got a higher power, then that function grows faster. And we can even compare functions like the natural log of x compared to x to the sixth, compared to x to the x. We can compare those and it's pretty cool. So here's theorem 4.14, ranking growth rates as x approaches infinity. Let f is less than g mean that g grows faster than f as x approaches infinity, with positive real numbers p, q, r, and s, and with b greater than 1. We've got powers of the natural log of x grows slower than powers of x, grows slower than the combination of powers of x times powers of the natural log of x, grows slower than higher order powers of x, grows slower than some number to the power of x, grows slower than x to the x, that tower function we were mentioning earlier. And that's it from me today.